Hello. All right, Chapter 22, Chemical Kinetics and Equilibria. First of all, these two topics, kinetics and equilibria, are something that we spend a whole college semester on in AP Chemistry. Basically, one large chapter on kinetics and followed by 8 chapters on equilibria, and they're going to kind of cram the basics of it into 1 or 2 chapters. This The acid-base chapters are really an application of equilibria chemistry. So, they're trying to deal with a lot of information in one small chapter. So I may wind up splitting this into several small tests, but as of right now, I'm still probably going to keep it one big test. Any event, chemical kinetics and thermodynamics. So there's two aspects of chemistry that are important, and especially in terms of application in technology and in business, etc. It says how fast do you reach a stage where you're able to harvest your products, and two, thermodynamics, how much energy does it cost in order to create these products? So, simple business principles here. Time is money, and profit is based upon your margins. So, these are two very important practical aspects of chemical reactions. So, they introduce two different constants in this chapter. So, I'm going to go to that. Oh, here we go. Okay. All right, first of all, kinetics. They introduced lowercase k, and lowercase k is called the rate constant. Rate meaning how fast. Yeah, I just gave you the definition of rate. Rate constant. And what k considers is how fast do we reach what we call a position of equilibria. So we'll have to discuss what equilibria is in just a moment. But in other words, k describes how fast do you get to your completion of the reaction, or do you get to the completion of the reaction? That's funny. That looked like how fart. It's how fast. Okay. The things that are considered in the rate constant is things like the activated complex. In other words, we got to bring together reactants. They have to come together at the right time, right place. So, reaction timing, reaction site, bring together at the right time, right place, correct angle, because these are based on particle collisions, so we're looking at angle of collision. And when we talk about reaction site, we mean usually something called a functional group, which we talked about in chapter 13. Right time, right place, correct angle. Right time, right place, correct angle. This is driving me nuts. My knuckle is laying against this and it's erasing everything that I'm writing. And it's hot up here and I have to turn off the air conditioning in order to be able to be heard. All right, enough of my complaints. Right time, right place, correct angle on the functional group, and it has to have enough energy to break bonds. So K considers that. And K also takes into things like the amount of surface area for a reaction. It considers things like reactant concentration or reactant amount. And if it's a gas phase reaction, it also takes into consideration pressure. And we have to also consider the thermal environment, how much heat. And last thing, fifth factor that we have to consider when we talk about rate constants is we have to talk about the presence of a catalyst. Is there something that's going to help speed up the reaction? So when we talk about kinetics, we're answering the question, how fast? How fast do we reach a position of equilibria? And we use lowercase k in our calculations called the rate constant. And the rate constant considers things like activated complex, surface area, reactant concentration, thermal environment, catalysts. It depends upon how you set up your data and how you're doing the calculation itself. The second factor we said was thermodynamics. And when they talk about thermodynamics, they introduce capital K, and this is called the equilibrium concentration. Numerically, the equilibrium constant is equal to the concentration of your products over the concentration of your reactants at equilibrium. So for stoichiometry, we have almost 100% product yield, so K is infinity. It would be 100% over 0%, so you get undefined. Most reactions don't proceed that way, and we'll talk about that in a few minutes. But when you talk about thermodynamics, you really have to consider a couple of things. Are these products that you're creating, are they thermodynamically favorable? In other words, what is the enthalpy? Are you going from high energy to low energy? Are you going from low energy to high energy? In other words, things like exothermic materials tend to be more thermodynamically stable because we're going from high energy reactants to low energy products. Now, that's not to say you can't go in the other direction, endothermic. You certainly can go endothermic. But exothermic materials tend to be more thermodynamically favorable. The other thing that we should consider is entropy. Entropy is the amount of randomness. And it can be things like particle motion. Gases have more entropy than liquids, which have more entropy than solids. Things that are entroscopically favorable tend to produce more randomness. I mean, there's a lot of exceptions to that. Crystals, for instance, are very ordered in structure, but yet very thermodynamically stable. So when we talk about thermodynamics and we say, well, something is thermodynamically favorable, things that are exothermic tend to be more favorable. Things that produce randomness tend to be more favorable. But there are lots of exceptions, because the third thing that you have to consider in thermodynamics is you have to consider the thermal environment. And we could put this all together in an equation called the Gibbs-Helmholtz equation, where delta G is equal to delta H minus T delta S. Delta G talks about spontaneity. Delta H would be the enthalpy, and T is the temperature in Kelvin, and delta S is the entropy. So that's a lot to have to deal with here in one chapter. In terms of kinetics, we have to deal with the rate constant and how to do those calculations. There are a number of different ways of doing it. We're only going to learn one way in this class. And we have to consider all the factors that affect the speed of a reaction, like how the activated complexes form, bringing things together at the right time, right place, correct angle on the functional group with enough energy to break bonds. We have to consider surface area if it's a heterogeneous reaction. What is our reactant concentration? Certainly high concentration materials are going to have more particle collisions than low concentration. What's the pressure? How much heat do we have? Is there a catalyst? So there's a lot of different things there just in kinetics. And then when we talk about thermodynamic equilibria, we have to consider not just the calculation of how much product we have versus reactant, but we have to consider the thermodynamic properties that lead us to that equilibria constant, which is the enthalpy, the entropy, and the amount of heat energy in the environment. So again, this is a big chapter and there's a lot to it. It's not an easy chapter, it's not a lightweight chapter, but it's one of my favorite chapters, and I think it's very interesting. All right, so we'll start with kinetics. Different reactions take place at different rates. The ones that we've been dealing with in our class so far this year have been things that were instantaneous because we only have an 88-minute lab session. But if you get into organic chemistry, it's sort of like baking a cake. You know, cooking different foods takes different amounts of time. Things aren't generally instantaneous. So different reactions take place at different speeds. Things that there are certain trends, things that tend to be stoichiometric in nature tend to be a lot faster than things that aren't, but we're going to find that we have some trends. We don't have any absolute things that we can follow because we're talking about 14 million different chemicals and not all of them are going to follow all of these simple rules. They introduce this idea of spontaneous versus non-spontaneous and they assume you know what they're talking about. So just as a review, when we say that something is spontaneous or non-spontaneous, we don't mean possible versus impossible. Just because something's non-spontaneous doesn't mean it's impossible. It just means that we're waiting for energy. We're waiting for you to input energy in order to make it happen. So, although non-spontaneous reactions tend to be more expensive than spontaneous meaning that they happen without you adding the energy, non-spontaneous are a lot easier to control in the lab than spontaneous and tend to be a lot safer. So again, spontaneous versus non-spontaneous. If you take an ice cube and throw it outside, on a cold day, it's not going to melt. Now, to melt ice, you have to add heat. The choice is, well, does it get the heat from the thermal environment to melt the ice, or do you have to add the energy to melt the ice? So on a day where it's below the freezing point, you throw ice outside, it doesn't melt spontaneously. That doesn't mean it's impossible to melt the ice. It just means I got to hook up a heater or a hair dryer or something and blow hot air over it to make it melt. I mean, it can happen. It's just waiting for me to add the energy. Whereas something endothermic like melting ice can be spontaneous. And today, for instance, it's nice and warm. It's about 80 degrees outside. So you're looking at spontaneous melting. It's going to happen without you doing anything. So again, the mistake people make with spontaneous versus non-spontaneous is that they start to think that non-spontaneous is impossible. It's not impossible, just means it's waiting for you to add the energy. Another mistake people make, spontaneous versus instantaneous. Something can be spontaneous doesn't mean it's instantaneous. If you have a large chunk of ice and it's only 35 degrees Fahrenheit outside, it's going to take a long time to melt. It will be spontaneous, but it won't be instantaneous. So the book introduces the term thermodynamically stable, and I don't like this term. I have to go over it. It's in the curriculum, and I'm going to put it in here and be a multiple choice test question. But I prefer the term thermodynamically favorable. Is something thermodynamically favorable? Does it have the right conditions of enthalpy, entropy, in order to make a tendency for the products to form? But they talk about thermodynamic stability, meaning can you control it? Well, as a general rule, if you're going to control it and it's going to be stable, it has to be non-spontaneous. Now, be careful with this. Most things that are non-spontaneous tend to be endothermic, but there are certainly exothermic reactions that are non-spontaneous. But as a general rule, endothermic tends to be more spontaneous than exothermic, which means that you're looking at a positive delta H. Remember, delta H is the heat of the products minus the heat of the reactants. So the products are at higher energy than the reactants, which means they're thermodynamically less favorable. So thermodynamically less favorable tends to be thermodynamically stable, but there are exceptions. Kinetic stability. just because something proceeds spontaneously doesn't mean instantaneous. In fact, some reactions are so slow that you can't detect the change, and if it's that slow, we say that it is kinetically stable. Kinetic stability is pretty rare. So this chart just kind of sums it up, and if you're copying this chart in your notes, do understand I'm limited by my use of the software. So for instance, in the column that says Spontaneity, it is not Spontaneity. It is Spontaneity. Same thing with the word below it. It's not spontaneous. It's spontaneous. I could go back and fix it, but I'm lazy. So, again, summarizing, exothermic reactions tend to have a negative, R negative delta H. They tend to be spontaneous, so be careful with this. And in fact, I'm going to put, a little star next to it, right? Tend to be spontaneous. Endothermic tends to be non-spontaneous. So I'm going to put usually, right? Not always. And again, thermodynamic stability. If something is spontaneous, then it's happening, it's unstable, you're going to have difficulty controlling it. And if it's non-spontaneous, that means it's thermodynamically stable. Again, not necessarily favorable or unfavorable, though. There are a lot of things to consider. All right. Equilibria itself. We're used to taking a look at reactions stoichiometrically, where we're only considering one process. All reactions actually undergo two processes, something we call the forward reaction and something we call the reverse reaction. However, in stoichiometry, the forward reaction is so dominating that we don't really consider the reverse reaction. However, most reactions on our planet are what we call reversible reactions, where we have to consider what's happening in the forward direction and we have to consider what's happening in the reverse direction. So in other words, we're used to taking a look at reactions and saying, all right, these reactants produce products. Well, we know from the Maxwell-Boltzmann distribution that not all the particles are moving at the same speed. So what happens when an extremely fast-moving product hits another extremely fast-moving product? Is there enough energy there for the bonds to break and for the material to revert back to reactants? And the answer is absolutely yes. So for most reactions, we reach a condition where, yes, reactants are forming products, but in the same sense, some of those fast-moving products, some of the ones that are beyond the X-bar norm, are breaking apart and reverting back to reactants. At some point, we're going to reach a period where we no longer detect a change. In other words, the forward process is occurring at the same speed as the reverse process, and that's where we talk about dynamic equilibria. So, a couple of things. If we're dealing with stoichiometry, in terms of product yield, we say that our product yield approaches 100%. So when we write a reaction like A plus B, we use a single arrow, and that single arrow means that this is stoichiometric, where we are considering the forward reaction only. And since our product yield is 100%, if we set up a value for capital K, or what some people call KEQ, meaning products over reactants for a general equation, and we set up our concentration of our products over concentration of reactants, well, if we get a stoichiometric yield, then we're approaching, I'm going to put a little mark here, approaching 100% products, which means we're approaching 0% reactants, which means our KEQ value approaches infinity. And if that's the case, then there's no sense in considering what we call the reverse reaction. So in stoichiometry, the only thing that we've been doing is considering the forward reaction. So again, A plus B produces AB. We would call that the forward reaction. However, most reactions on our planet reach a condition of equilibria where some of that product bangs around, breaks back apart, and so you get the forward reaction, right, forward, A plus B produces AB, But at the same time, the reverse reaction, AB breaking apart into A plus B, is occurring. So this occurs simultaneously in equilibrium, the same rate. So when we write an equilibria reaction instead of stoichiometric, the only difference is we use a double arrow. So if we're talking about a condition of equilibria, A plus B produces AB. We use that double arrow to represent it, which means that we are considering the forward reaction and the reverse reaction in equilibrium. So the double arrow means equilibrium. Now, in terms of KEQ, all it means is that our product yield is less than 100%. So what this means is KEQ, is not equal to infinity. So again, that means product yield does not approach 100%. Okay, so I got this video that explains equilibrium reactions. It's from TED Talks. I think it's a pretty good video. However, I noticed when I tested recording it on here, there is an echo that comes out behind it. I do want to go through it. It's only a 3-minute video, and pause it at certain points to kind of explain a couple things at the end. So I'm also going to post this this link on Edmodo, and if you want to watch the video there first and then come back to this, you can. I mean, I listened to it and I thought the echo was annoying, but I didn't think it made it unwatchable.
I cannot think of any line of work that you are not going to benefit by communicating effectively.
Skip ad.
Say two people are walking down the street and they bump into each other. They'll just shake it off and walk on. Sometimes that happens with molecules too. They just bounce off each other and that's that. But what if two people were to bump into each other, and during that collision, one person's arm got severed and reattached to the other person's face? Now that sounds really weird, but it's similar to one of the many ways that molecules can react with each other. Two molecules can join and become one. One can split apart and become two. Molecules can switch parts. All these changes are chemical reactions, and we can see them happening around us. For example, when fireworks explode, or iron rusts, or milk goes bad, or people are born, grow old, die, and then decompose. But chemical reactions don't just happen willy-nilly. Everything has to be right. First, the molecules have to hit each other in the right orientation. And second, they have to hit each other hard enough, in other words, with enough energy. Now you're probably thinking,
all right, so right time, right place, correct angle, usually a functional group, with enough energy to break the bonds, is what they're saying happens.
that a reaction just happens in one direction and that's it. Sometimes that's true. For example, things can't unburn or unexplode. But most reactions can happen in both directions, forward and reverse. There's no reason that our face arm guy can't bump into armless girl, reattaching that arm back to its original socket. Now let's zoom out a bit. Now let's say that you've got 1,000 people on the street, and all of them start with their limbs normally attached. At the beginning, every collision is a chance for person A to transfer an arm to person B's face. And so at the beginning, more and more people end up with arms attached to their faces or arms missing. But as the number of people with arm faces and missing arms grows, collisions between those people become more likely. And when they bump into each other, guess what? Normal appendage people are reproduced. Now the number of limb transfers per second forward will start high and then fall. And the number of limb transfers per second backward will start at 0 and then rise. Eventually they'll meet.
Now, I don't disagree with that. I don't like that they say that they're going to meet. They don't necessarily meet. The reason why the forward reaction is so fast in the beginning is because you have almost nothing. Well, you have nothing but reactants. So what are the odds of a collision occurring among reactants? It's very high. And if you haven't produced any product yet, it explains why the reverse reaction has a speed of 0 to begin with. You don't have any products to break back apart. So as reactants turn into products, your collisions among reactants slow down, and you get more collisions among products, speeding up the reverse process. Eventually, the two processes wind up with the same speed, but I don't like this graphic because it implies that 50% of your reactants turn into products and 50% of your products turn into reactants, and that's not true. Some reactions produce a lot of product, and some reactions only produce a little bit of product, but eventually the slope, they will be parallel to each other.
Meet, they'll be the same. And when that happens, the number of people in each state stops changing, even though people are still bumping into each other and exchanging limbs. Now, how many people do you think there are in each state? Half and half, right? No. Well, maybe. It depends. It could be 50-50, but it could be 60-40 or 15-85 or anything. We chemists have to get our little gloved hands dirty. We're in a lab, so not really dirty, to figure out what the actual distribution of molecules is. Even though each of these limb transfers is a pretty dramatic event for the people involved, if we zoom out, we see population numbers that don't change. We call this nirvana equilibrium, and it doesn't just happen with chemical reactions. Things like gene pools and highway traffic show the same pattern. It looks pretty still from 30,000 feet, but there is lots of crazy stuff happening on the ground. You just need to zoom in to see it.
Okay. All right, so again, that whole equilibria thing, yes, eventually you're going to get to a point where the reactants are changing into products, and at the same pace, the products are changing back into reactants. Same sort of thing we had when we reached thermochemical equilibrium. Same condition we had when we had phase change equilibria between evaporation and condensation. Our forward reaction is going to be occurring at the same speed as our reverse reaction. At that point, it looks like the reaction's done to us on a macro scale level. But that doesn't mean you get 50% reactants, 50% products. It depends upon which one's more thermodynamically favorable. If the products are highly thermodynamically favorable, you may get 92% products and let's say 8% reactants. But if you get that your products are unfavorable, you might get 1/10 of a millionth of a percent product and the rest reactant. And that might be worth studying. For instance, how much lead poisoning and how much lead ion contamination does it take in order to cause brain damage? It's only a few parts per billion. And so even though you have a really small yield of lead ions that come from, let's say, the lead iodide we made earlier in the year, it's still biologically worth studying because it doesn't take much of a yield in order to have a large biological impact. So here's a chart I made. Here's one reaction where we started out 100% reactants, 0% products. And as we started to run out of reactants, as they turned into products, the forward reaction, red, reactants becoming products, slowed down. And the green, which is products becoming reactants, the reverse reaction sped up. So I'm going to label that this is my forward reaction here in red. Reactants becoming products, and the green is products becoming reactants. Reverse reaction. Eventually, the slopes are equal. And then you've reached the position of equilibrium. So this would be an example of a reaction that reached equilibria when we had a yield of about 65 to 70% products. I'm sorry, 65% reactant, 35% product. But in a different reaction, where the products are more thermodynamically favorable, you might get this graph. Eventually the slopes are parallel, but they become parallel after 80 to 85% of the product has been formed. Or you got 85% product and only 15 to 20% reactants at equilibrium. So it depends upon the reaction itself where you get this position of equilibrium. Reversibility implies that there's always some reactant present even after products have formed and that you can't get 100% yield. That makes sense. because you're always going to have in that Maxwell-Boltzmann distribution of particle speeds fast-moving products that hit and break back apart. All right, so I'm going to stop here, and in the next video, I'm going to start to take a look at how reaction rates are determined and the factors that affect the speed of a reaction. Thanks.